So let's do this. Let's do the last lecture of ISS2025. Would you please make very welcome, in the usual fashion, of slapping your hands together loudly for Professor Donna Strickland.
All right, so yesterday your speaker was Donna Strickland, the Nobel laureate. And the Nobel laureate gets to have a team of communication specialists help her with the Nobel talk, which is the talk you heard yesterday. But today you just get Donna Strickland, the professor, and the talk is prepared by the professor all by herself. Okay, so the slides will not be quite as good. There are no dancing photons in these slides. So this is also, yesterday's lecture was about the research I did while I was still a graduate student, and this talk is more about the research I do as a professor at the University of Waterloo, which is up in Canada. So it's about making short pulses. Yesterday I talked about how I wanted to amplify short pulses. Today is about wanting to make short pulses, and pulses a bit shorter than what can come out of lasers themselves, but not really attosecond pulses, which is the shortest today. So this is what we're going to talk about. So why first do you want to do it? And the reason that we're trying to do it is to make molecular movies, so I'm going to explain that too. But people for a long time, you know, more than about 150 years, people have been trying to stop action so that we can see things that are happening too fast for our eyes to see. And horse racing was one of those things. And of course, sometimes our eyes see it, but there's no proof for you. If your neighbor didn't see it, you simply saying that you saw it doesn't cut much mustard. So for whatever, some kind of horse racing, and I'm not sure I know the whole story, but the different types of horse racing, you were supposed to have all of your horse's feet off the floor at the same time, and people didn't really know if that was happening. So Edward Muybridge came up with a scheme that he set up a lot of cameras along the race course, and he had them timed to the starter pistol so that they would take the pictures in rapid succession, and he was able to show somewhere now. Oh, there it is. Oh, hang on. Oh, is this a different one than yesterday? And how, it's not nearly as bright as yesterday's. Oh, well.
I've got the bright one here. If you
Do you have the bright one? Oh, yeah, okay. We can all see green better than we can see red. Okay, thank you. Okay, so here's the one where it shows that indeed all of the hooves are off the ground at the same time. And so he was able to stop the action of a horse running. So the time scale that you need is to be a millisecond, and so that's the speed of a camera shutter. And you can stop the action of a horse because a horse is a fairly massive object, and so it can only move so fast. But what if you wanted to measure something moving even faster? Well, if you go forward about 50 years, Harold Edgerton was the one who realized that you can't make shutters go any faster. It's also got mass, and so there's a speed with which you can move shutters open and shut. But instead, if you keep the room dark and only have a flash of light, then the only light that can come to the camera is from that short flash of light, and that stops the action. So now they're able to stop a speeding bullet, as you can see here, and you get to see what happens to the poor apple when a bullet goes through it. And so this is now in the mid-1900s. We have microsecond timescales, right? So now what are we trying to do these days? Let's talk about trying to make a movie of the motion of the atoms of molecules, all right? Now, I will have spectroscopy colleagues tell me we don't need your short pulses to do that. We know all about the the frequencies from our spectroscopy. But we're talking about watching something dynamical happen, cause some kind of event in a molecule, and see how the energy goes through it. So what do we need in order to be able to see a molecule? Now, again, this is just my rendition of this. And atoms aren't necessarily balls connected together by strings, but let's go with that. And so I'm showing CO2, apparently. And it can either vibrate, and this would be the asymmetric stretch, and our spectroscopy friends would be able to tell that one too, or it could be this one. So, and these will move, on the order of tens of femtoseconds. If you had hydrogen there, hydrogen is the lightest of the atoms, and so it will vibrate on the order of 2 femtoseconds. Femtosecond is 10 to the minus 15, or a millionth of a billionth of a second. And so in order to stop that action, you actually need the light pulse to be shorter than that. So this is why we want pulses on the order of single femtoseconds, so that we can actually watch the motion of the molecule. Now, the other thing, though, to notice, although because this is just, that ever sticky note, don't worry about that, is that you cannot just have your femtosecond flash of light and see this happening, because the atoms are way too small to be seen by a normal microscope, right? So you're not just attaching a camera to your microscope in order to do this, so you need something more than just the short pulse of light. So how are we going to see it? We're going to use something called Coulomb explosion imaging. So that's what I'm going to describe before I explain how to make the short pulses. And so what we're going to really do is just try to determine the distances between the atoms. We're not actually going to image the atoms. We're only going to be able to measure what is the center of mass distance between the atoms. All right, that's the goal of the project. So what is Coulomb explosion imaging? So let's say now we're going to go to a molecule. This is 2 atoms to explain this. And we're going to go in with a short pulse. It's going to be shorter than the vibrational period so that there's stopped action. And this short pulse is going to have to ionize. It's going to have to strip an electron off of both atoms. And so this is what I ended my talk with yesterday, is that with now energetic short pulses that have been amplified by CPA, is strong enough to strip those electrons. That's my laser hammer. We'll strip the electrons off of each of these atoms. So we don't need just short pulses. We need high energy pulses. But the pulses have to be shorter than what can come out of a laser. All right, so now to explain this, just in case you don't... Really? Oh, okay. No, never mind. All right, so hopefully you've all seen the pith ball experiment. Does anybody not know the pith ball? Not seen the pith ball experiment? Okay, so somebody has shown you, you rub rubber with a silk or something, and you put charges on pith balls. And pith balls are these very light balls, and they come apart. And so it was Coulomb, way back hundreds of years ago, that did this work and showed how the electric force between 2 charges is inversely proportional to their distance squared, and the energy of the system is inversely proportional to 1 over the distance between them, okay? So now usually a pith ball, though, you have to remember, are sort of millimeter-sized balls, and so the center of mass to center of mass is at least 1 millimeter apart, and so that's actually a fair distance apart. So if you say, what's the Coulomb force, you know, you watch them go apart, but the tension on the strings is enough to hold them there. But now we're taking atoms in a molecule, and so those atoms are sitting just angstroms, or 1/10 of a nanometer apart. Okay, and so it's only, 10 to the minus 10 meters apart, and the energy of that force is that 1 over that distance squared. So if you have 2 charges that close together, they cause an explosion between the 2 of them. And that's why we call it Coulomb explosion spectroscopy. So I've been talking about both the force and the energy. The other thing I want to be careful of is what we're going to measure is we want to measure the potential energy of that system of 2 charges, and that will give us the distance between them, if we could measure the potential energy. But you can't actually measure the potential energy. You can measure the kinetic energy. But again, what you learn pretty early in physics is that really what physics is about is one kind of energy turning into another kind of energy. And so if you want to unfortunately you guys don't have winter here. I don't know. I watched all those countries. Maybe if you come from the United States, you actually have winter. You have winter? Excellent. All right, so those of us who come from countries with actual winters will go skiing and enjoy our actual winters. But we want to have the fun skiing down fast and getting the kinetic energy increased by going down the hill. But very few of us want to walk up the hill, and so we have some kind of lift To do the work it takes to fight that gravitational force, and you do work to get up to the hill. Once you're on the top of the hill, you've now stored that energy. It doesn't matter how long you stay on that hill. You can pick up the kinetic energy whenever you decide to go down the hill, okay? And so forgetting all of the losses that we're not going to worry about, potential energy is given by the kinetic energy, and it goes back and forth. So what we're going to do is measure the kinetic energy, and you can work back to then say that's what the potential energy had to be. So this is how it works. We have a molecule there. We're going to go in with our short, intense pulse. We're going to ionize both of them, one charge on each atom. Then we're going to let it fly apart. There it's going to fly apart on its own. And you're going to measure then the final speed. So you now know the speed, which is the kinetic energy, and you also, with your detector, know what direction they went. And so by knowing what direction they both went, you know what line they were along, and you also know how close they were. So that's how we're going to make our molecular movies. And here's just a cartoon. It's from Daniel Strasser's group at the Hebrew University of Jerusalem, who came up with this slide. And he's given me permission to use his slide. So this is a hypothetical, just 4-atom molecule. I don't think you can see it there, but it says there's a cloud. The cloud is of electrons. All right. So just like Muybridge watching the horses run, we have to have a starting pistol. And so we have one short pulse that causes some reaction. Okay. Time to that pulse, you'll have a second short pulse, and it will start probably timed before this one. You would measure, it would look like this. And then, each shot after shot after shot, you change the relative timing of this one to that one, and you watch what happens to the molecule as the energy gets dispersed. And then, because of the Coulomb explosion here, this one is just showing that one atom would go this way, one atom would go this way, and these two would stay together. I guess they're actually rotating, but flying off that way. And so from that measurement, you can see how close they all were when they were together. So that's what we want to do in order to make our molecular movies. So to do this, and my colleague, my lab is right beside Joe Sanderson, and he is an expert in this. He's still waiting for me to make the lasers that we want in order to do this. Okay, so I showed this slide yesterday, so I'm just going to remind you that in order to have a short pulse, you need a lot of colors. So let's talk about having all these colors. There's going to be one fundamental wavelength or frequency. So there is a period of time from a peak to a peak. The frequency is then given by 1 over that time period. All right. And if you add a bunch of frequencies that are all what's known as harmonics of this frequency, so this is twice the frequency, 3 times the frequency, 4 times the frequency, 5 times the frequency. And again, I made this PowerPoint slide, and it's not scientific or well made. So I'm just going to show you that this is just my rendition of saying that right here, they all add up as a peak, so you get a peak. Here, there is a mixture of destructive and constructive interference. If you had more and more and more of these frequencies, this would get closer and closer to being perfect zeros between the pulses. The other thing to note is that if you have these frequencies that are harmonics of the fundamental, you then have a series of short pulses, and the time between the short pulses is equal to this delta t of the fundamental, peak to peak, the crest of the fundamental frequency. So the one thing to note is that this is, I'm going to be explaining Fourier transforms to you, is that if it's delta t, giving you delta t in time, the frequencies are going, the differences in frequencies are going by 1 over that time period, okay? This is the real thing to know about this talk. If it's in frequency space, going to time space, you take this spacing and just make it 1 over, all right? This is, I'm sure you've all heard of Heisenberg uncertainty principle. Everybody heard of Heisenberg uncertainty principle? No? Yes. Yes. It's because it's the International Year of Quantum, you have to. It really bothers me that Heisenberg gets his name attached to that, because the reason Heisenberg uncertainty principle is the Heisenberg uncertainty principle is that every object is also a wave, and it's just wave theory. So I don't quite know why he got his own name attached to it. It is Fourier transform theory is all it is. All right, and so that's what it is. All right, so we want a lot of colors so that we can get these close to zero as possible, and also we get this as short a time as possible. The thing is, this is what comes out of my mode lock laser that I talked about yesterday, and these pulses then go on for a long, long time, so the energy per pulse is not very big, and that's why I had to amplify it. Now again, coming out of all of these lights are all of these colors, but there is no mode locker in the lights, and so there is no way to have them all timed, and so you would just get noise out. All right? So it's important that you have all the colors, the harmonics, and they're timed up. So how do we get these phased periodic frequencies? And the first one that I already discussed yesterday, but without really explaining it, is laser mode locking. So yesterday I also said that one of the reasons that we have a cavity around our laser to send the beam back through the material in order to get the energy up, but that was only one of the reasons. The main reason is this, is that we actually want to set up cavity modes. So there are two mirrors there, and they only allow certain frequencies to laze, okay? And so this is the same thing as if you do a standing wave pattern on a string. You want to use this constructive and destructive interference to set up certain wavelengths to laze, and only those wavelengths to laze. And so here it is. If you have a length L here, the fundamental wavelength is twice that length. So this would be a wave going down, it would come back up and be over here. That would be one period of that. But because it's got a mirror, instead of going on this way, it bounces, comes up, and it meets itself. And because it's exactly that 2L in length, it comes back and meets it back exactly the way it started, and it only constructively interferes. Every round trip, it constructively interferes. Any wavelength that is then a multiple, well, 2L divided by n, an integer, this will happen. So the green one I've shown you is one wavelength, two wavelengths, three wavelengths, four wavelengths equals L. And so it would also be allowed to laze. And so again, this will be the fundamental frequency would be C over 2L. And then you'll see that we automatically make harmonics of all of those frequencies by having this cavity. So theoretically, when people study mode locking, they show it the way I showed it. They show all of these frequencies, and they will do the math of adding up all of those frequencies, and you will result with the mathematical description of this periodic short pulses. But if you're an experimentalist like me and you're in a lab trying to make it work, you're not thinking, how do I time up all of these frequencies, because you can't see them anyway. And so you don't think about mode locking that way. You think about mode locking in the time space, and you're trying to set up a short window of time. But what this really says is if you do have them all locked together and you make this short pulse has to travel at the speed of light. So we'll assume it's going this way first. It goes this way, comes around, comes back, and it just keeps rattling around this short pulse inside the laser cavity. Now we want the light to come out of the laser cavity, so they are not 100% mirrors. One of the mirrors usually lets maybe 2% of the light go through. So when the pulse gets to here, it lets 2% of the light go out. It circles back around, comes back, and it lets the next pulse out. And so you can see these pulses in space are 2L apart, and in time, it would then be 2L over C. And so this is a beautiful way of seeing the mathematical Fourier transforms in that the cavity is letting exactly these frequencies be there, and the round trip time is connected to that, and this is how the pulses come out every 2L. All right? So if you wanted a single color laser to do high resolution spectroscopy, which is the opposite of what I want, you would make sure that the spacing of those frequencies was wide enough that the gain was narrower and you would only get one cavity mode. For those of us who want to have short pulses, we want as wide gain spectrum as we possibly can to have as many modes lasing at the same time that we lock together to make our very short pulses. And so when I was working on CPA in the mid-'80s, Peter Moulton was working on this new type of laser crystal, titanium doped sapphire. This, to this day, remains the widest gain spectrum that we have. So my laser, when I was doing the picosecond work, was just 4 nanometers wide. But now we have a laser gain that's actually about 200 nanometers wide. This is the widest, or it's about 100 terahertz in frequency. All right? And so this laser made pulses a lot shorter than in my day. And we now have laser pulses that come out of a Ti-Sapphire oscillator at 5 femtoseconds. Okay? So that's almost as short as what I said we wanted to even see hydrogen go back and forth. We want 1 femtosecond, but a laser can give you 5 femtoseconds. But we don't want the energy that comes out of a laser, we do have to amplify it. And so we cannot keep the pulses that short when we amplify. And the reason is that here's the gain curve. Doesn't matter which one of these you look at. So let's say the oscillator comes out and you have this huge bandwidth, and that will make a short pulse, all of those colors. But then you go to amplify them, and the center color gets to be, this guy gets to be amplified twice as much as these two guys. And so if you actually let that one go up a factor of 2, this one would only have gone up half that amount, and you would get narrower. And if you wanted to amplify it 1,000 times, of course, it gets narrower and narrower and narrower. And if the spectrum keeps getting narrower, the pulse has to get longer. So people have used some tricks to get around this, but amplified short pulses are no shorter than 25 femtoseconds right now, maybe 20, but I'm going to go 25. And so that is too long to do our Coulomb explosion imaging, at least of the lightest atoms. So we want to be shorter than that. On the other hand, we have, I also said yesterday in my talk that I was hoping to see the 9th harmonic, okay? And my experiment was blown out of the water. And it was really about this woman's work, Anne Lullier. Yeah, there she is, Anne Lullier. Now, this is work she did in the 90s, but the work she did in the 80s was she had already seen the 33rd harmonic, okay? And so, and it was this flat line of them. They just went on and on and on, and now you can see that by 93 she had 100 of them. Okay. Now these look like they're getting closer and closer together, and not, you know, absolute frequencies. And that's because, again, theorists only talk about frequencies, but experimentalists only measure wavelength. It's a weird thing, but that's the way it is. So what we can measure is wavelength, and so it's being plotted there as wavelength, and that's why the frequencies, which are 1 over, are getting closer and closer together. But luckily she has pointed out for us, as you know, that's the 47th, the 57th, the 67th, and that's the 97th. So each one of these peaks has the same frequency difference between them, and it's actually twice the fundamental frequency of the laser itself. And so this is an enormous amount of bandwidth, and because they have this enormous amount of bandwidth, they actually were able to figure out how to phase all of that bandwidth together, and they have the shortest pulses of any kind of pulse that we can create on the Earth of now about 50 attoseconds. And this, of course, is what won the 2023 Nobel Prize for these 3 people. So I've already pointed out that Anne was the one who's really led the charge in figuring out how to make the harmonics. Franz Krauss was the first one to figure out how to phase all of that and get it to be a short pulse. And Pierre Agostini was the person who figured out how to measure that something was an attosecond. Because until you have attosecond pulses, you don't really need to measure attosecond pulses. And so this was a whole long study in itself, was what can we use to even measure that something is so short. And so he's a multiphoton physicist. He's the one who taught me the difference between nonlinear optics and multiphoton physics. But he's the multiphoton physics person and figured out a way to measure how pulses are short. So these, I do not work in the attosecond field, and so that's all I'm going to tell you about that. So we have amplified short pulses that get you to 20 or 25 femtoseconds. We have pulses so short, down to 50 attoseconds, they can actually watch the electron motion. But I'm kind of like Goldilocks. One's too long and one's too short, and I want to be something in the middle. So I'm going to work on something. Oh, I have to tell you this first. Should I tell you this first? No, I'm going to show you this first. No, I'll go back, because I already told you my Goldilocks story. This is what I work in. It's multi-frequency Raman generation. Again, because I talk always about how much fun I have working in the lab, this is one of these really fun experiments to do, because out comes every color of the rainbow. And it doesn't look nearly as beautiful here, because all I can use is color photography. And in color digital photography, they have their 3 filters to help pick out what the colors are. But I can tell you the 3 types of cones you have in your eye beat the heck out of anything they've got in camera technology yet. So in our lab, we actually can see every color. Now this one, we can't see, it's infrared, but silicon cameras can see out to 900 nanometers. This is 820 probably nanometers, so we can't see that. We can't see till 700. But these would not all look like the same color of yellow to us. We would see it go from red to orange. We would see it then go to yellow, and we would see different greens. This color is not even a real color. Okay, that's just something cameras make up. And so it would continuously go, and we would finally see the violet. And so it's just a beautiful thing to see. And you can see it. Now, of course, I'm a little worried that probably all those colors are above eye safety, and we only are wearing infrared goggles, which is why we see all the colors. So next time we do it, we're going to do it safer. But it's still fun to see. And this one is my favorite of the spectrum of the kind of thing we're seeing here. It's the broadest of them all. I won't maybe explain it, but they can see many more orders than what we can see. But again, let me just go back. So the other thing that I want to talk about, and this sort of keeps going on with the Fourier transforms, is that the mode lock laser had these cavity modes. So they were separated by 0.1 gigahertz in frequency, and that would give you 1 over, and so that's 10 nanoseconds. So the pulses come out of our lasers, Ti-sapphire lasers, every 10 nanoseconds. The biggest thing in this one is the overall bandwidth of the laser, and let's say it's 10 terahertz. That would then give you 1 over the 10 terahertz. The 0.5 is there because it's a Gaussian beam, but that gives you the 40 femtoseconds, which is fairly standard pulse duration for it to come out of a Ti-sapphire laser. But as I said, the smallest thing here is the width of this cavity mode, and so the pulses go on and on and on forever, and so the energy per pulse is not that high. On the other hand, in the higher order harmonic generation, it takes this whole bandwidth and turns into a single pulse. And so you have just one single pulse. It's this huge bandwidth here. And now we're going to have many of them. I've just taken, I think, 10 of them. And they're separated by 600 terahertz because the fundamental frequency is 300. Oh, am I losing the battery? I may be losing the battery. I'll go back to the red one. That's okay. Well, okay. So the 300 terahertz is the fundamental frequency, and you only get every other harmonic, and that's why it's 600 terahertz apart. If you take 10 of them, that's 6,000 terahertz. That enormous bandwidth is why the pulses get to be so short. On the other hand, because they're separated by such huge frequency spreads, you actually have the pulses coming faster than every 2 femtoseconds, okay? And so in a very short time, you can still have a lot of pulses. Now, the people working in the attosecond field have got this down so they can make almost just one pulse here and have all the energy in that one pulse. That's what you want, but I don't want pulses this short, and I don't want pulses that long. Oh, maybe I have to go back. All right, so mine's called multi-frequency Raman generation, so now I'm just going to explain what Raman generation is. And Raman was working long before the lasers came along. Raman found Raman scattering back in 1928, I believe. So in optics, it is a linear process. And what happens, I don't know if I can, oh, there, it's bright again. Just need to rest. So if the light comes in, and I think this will cause it in my way to make it vibrate. Yep, there we go. So if it vibrates more than it was vibrating before, that took energy. And the only thing we added was light. And so the energy had to come out of the light. And so the energy, remember, is in the color. And so it actually changes. And the frequency of the light is actually reduced by the amount of the frequency and the vibration. You can also cause it to rotate. And I couldn't figure out how to rotate the line. That's why there's no line between them. But anyway, the rotation's usually less energy, and it doesn't take as much energy out of the photon. Now, I find the quantum picture easier to explain, although I did have students ask me last night at the end of the gala about this. So let me just explain a little to make it clear. First, and the way I explained it to them was just to even understand what is the index of refraction. And why does light slow down in glass versus vacuum? And so what's happening in a quantum picture is that the light comes along and lifts the energy from this ground state up to this virtual state. The real states are way up here in the ultraviolet, but it lifts it this far and you have a virtual state. And this virtual state exists for a small amount of time, and the amount of time is given by how close it is to the real levels. And it is the summation of all the levels, okay? So I won't go into all the theory, but it's a small amount of time. The light goes up, sits, and then regular, for index of refraction, the light would just fall all the way back to its ground state, okay? And it is that phase delay that looks like the light is slowing down as it travels through. But now, if you have molecules that can either rotate or vibrate, and these are small energy transitions, then just heat, just thermal energy, can cause some of the population to go from this level up to this level. The light cannot interact with the level if there's no population there. There has to be some electrons in that state for the light to interact with them. But this is what Raman was able to realize, is that by going up here, it could come down, and if there was some small amount of population here, it could cause some small amount of light to come down to here and leave it in this excited, more population in this excited state. And so you can see now that this energy, given by height, is lower than this one, and that's how the light gives up the photon. And again, this is the linear effects. One photon interacts with this one molecule at a time, and it gives up the energy from the photon. Okay? So when the laser came along, though, it is a linear process, and that means if you turn up the power of the light, the Raman signal will grow linearly with that. So while it's growing linearly, what this means is that this photon is going up here, and instead of coming back down, it comes back to here. And the more stronger, and because a laser is stronger than light, you're doing a lot of this transition, you are actually moving a lot of population from here up to here, much more than what you would get thermally, okay? And so once you have a lot of population here, well, then your pump laser can say, well, I don't have to just absorb from the ground state. I can absorb from the excited state up to its new virtual state, and I can then go all the way back down, where probably still there's more population down here, and this is what's known as the anti-Stokes, and you can see the anti-Stokes gains this vibrational frequency. It's the normal laser frequency plus this vibrational frequency. And so now you get it. So when people first saw this, then they saw the pump frequency, the Stokes frequency, one lower by the Raman frequency difference, and now the anti-Stokes, which is one Raman frequency higher. This led to a new type of laser spectroscopy called CARS, Coherent Anti-Stokes Raman Spectroscopy. Which doesn't really spell out CARS, but I don't know, they didn't want to say anti-Raman or something. I don't know. Anyway, they call it CARS. And so there was this group in Japan trying to do CARS spectroscopy. And the idea with CARS spectroscopy is that you would use two lasers, one strong laser, and then probably use some nonlinear thing to get a second beam that's at a different frequency, and you can tune this frequency up and down, looking, because you don't know where this level is, that's why you're doing the spectroscopy, trying to find this level. And when you tune this just right, you will see this frequency come out. That's the point. So there was this group in Japan trying to do CARS spectroscopy, and they were trying to tune their second color, two lasers, and have the second one be tuned through the laser gain. And when they got the laser tuned over to the edge of the gain, up popped another line at the peak of the gain that they weren't expecting. And all of a sudden they had a two-color laser system, and just by one of these happenstance things, that matched a Raman transition. And so even though they were just looking for this one line, what they saw was 40. 40 lines came out. So nobody was expecting this, and I was asked this question in the last few days, you know, does theory drive science or does experiment drive science? And the answer was both. And this was one of the times that nobody thought this would happen, and they saw it happen. So then, of course, people had to go back and try to figure out, why did it happen? Okay? So they started this new field, and we've had to think about it. And the other thing to realize is that it sort of looked like this high order harmonic generation, where there was a large plateau of many, many, many frequencies. And yet it's not the same theory at all. So what is the theory? This one is really just the same third order nonlinearity. It's a third order nonlinear process because it's 1 up, 2 down, 3 up, and those 3 photons drive this one. So this is why it's called a third order nonlinear process. But this process is just a cascaded third order happening more and over and over and over and over again. So now you're going to go in not with 1 strong and 1 weak pulse. You're going to try to have 2 strong pulses. So you're going to drive it up, drive it down here, and you're going to move a lot of population, and you can move almost half the population up to here, okay? And so have equal populations. Well, once you do that, and you sort of then have this very strong signal here, your 2 strong inputs will drive this so that you have equal population, but now you've made this frequency, and you can pump it up and make an even bigger frequency. I'm sorry, what? That doesn't come all the way down. It comes all the way down. And you would make this frequency, but you can now drive this so hard, you have a lot of this frequency, and you would do it again and again and again. You also go to the red side and make it smaller and smaller and smaller. But for making short pulses, you want the central you can't be shorter than 1 oscillation. And 1 oscillation in the red, in the infrared where we start with Thai sapphire, is 2 femtoseconds. So you'd rather your central frequency be in the blue so that it's more like 1 femtosecond. So we only want to go towards the blue, so that's what I'm showing you. So you can also see that it's a sequential process and not like harmonics. High order harmonics, just with 1 atom, you would get all of those. There's no propagation. It doesn't have to happen over and over and over again. We do the experiment in a hollow fiber, and the infrared comes in, and remember that the camera actually sees the infrared. We do not. So we would see this come in and turn red, and then this would look white. By eye, this just looks like it's glowing white, but because the infrared is still the strongest, it sort of looks like it's red and barely yellow here. Okay? But you can see that as it travels down the fiber, it happens more and more and more. And so it's one of the ways we know that it's a sequential process. You make that one light, and then it can make the next light, and then it can make the next light. So back to my favorite group in this field, which is Masayuki Katsuragawa. He's the one who had that beautiful spectrum that I showed you. He's also the one who figured out that as you make all of these colors, all the colors are going through these molecules, and so there is dispersion. So all these colors are not traveling at the same speed. They're all traveling at their speed, and so they come out and they don't make a nice short pulse. But he figured out, or his group figured out, that you could just take these 3 different types of glass, they rotate them so that it can be a different amount of thickness that you go through each type. Each type has its dispersion. And you can take these 3 types of dispersion, put the right lengths of each of those types of dispersion, and absolutely cancel all the dispersion inside this cell. And so by doing that, the group was able to show that they could get sub-single femtosecond pulses, okay? And that's what these red ones are, with nice zeros in between them. But he's using nanosecond long pulses to do it. And so he's getting these nanosecond pulse trains, and you can see there's only 8 femtoseconds from pulse to pulse. So he's getting thousands of pulses, and so again, the energy per pulse is not that high. So you can use long pulses to do this, which is what Masayuki does, Katsuragawa. And so you have very narrow spectrum, and you have many of them. And so the smallest thing here gives you the longest thing here. And so because it's a nanosecond pulse causing this spectrum, you would have a nanosecond pulse train here, separated by maybe 100 femtoseconds. So like I said, thousands of them. You would have a huge bandwidth. So this is why he saw single femtosecond pulses, but not a lot of intensity. I work with short pulses to start with. And so because I start with short pulses to start with, my smallest thing in the frequency space is quite a bit bigger. And so what we're hoping to have, if we even have the same total bandwidth making the single femtosecond pulses, we'll have a very short train of pulses so that, I won't use it so much. The energy is all in the center pulse. That's our goal. We want to have most of our laser energy go into that one pulse in the center so that we have something like a microjoule at least of energy, but in the single femtosecond pulse. So that's one of the reasons that I'm doing transient MRG, but not really. The real reason that I'm doing it, and the real reason I even got started in this field, is that Leonid Losev, I think his name's there, yes, his name is there, back around 2000, I think, I don't know, it was a while ago. He contacted me and he said, I see you've just put out a paper about two-color CPA, which I'm going to show you. That would be the perfect laser for me to try my idea for transient multi-frequency Raman generation. Can I come over to Canada and do it? And I said, come on over. I love when people want to use my lasers. So he had shown in his theoretical paper that you got 1.5 times the efficiency using shorter pulses than long pulses, so that was good. And he also showed that if you could control the dispersion, that you got more and more orders. This is just showing you how many orders he looked out to get the 30th order or the 20th going to the red side. This is going to the blue side. So he wanted to come and see if this would work. So this is the laser that I had built, that I had built in 2000. Okay, so this is the first thing I did. And so why did I build a two-color CPA laser? So I had followed my husband to New Jersey because he had been at Bell Labs, and then I got the job at Waterloo, and he followed me and took an industry job. But when he left Bell Labs, he was allowed to take all of his equipment, and he had built this two-color Ti-Sapphire laser to do whatever he wanted to do with it. But since I brought it into my lab, and it's a unique laser, I thought, what would I do with it? I would CPA it. So that's what we did. So I won't go through CPA again, just to say that two colors come out of here. They're synchronized together. They were both 100 femtoseconds long. I stretched both colors. I amplified both colors. And then we compressed both colors. Okay, so we had this amplified two-color laser system. Yeah, there. And this is the data. So on the top one each is what comes out of the oscillator, and the bottom is what we were able to amplify. I think this fell off the grating. I don't know what that is. So we could move what two colors we had. And so we could pick two colors to match our Raman transition. So we took the two colors. We're using sulfur hexafluoride. This is sulfur surrounded by these 6 fluorides. And the Raman vibration we're going to use is the symmetric one, so all 6 fluorides breathe in and out, in and out, in and out. And so we don't have to worry about rotations because it's all symmetric that way. And so we really had one clear Raman signal that we were going to look at. And then we do, when we just set it up, send it through this hollow fiber that I showed before. Inside the hollow fiber is the sulfur hexafluoride. And it comes out, we can just put a prism there and send it to a white piece of paper, which is how we took the pictures, okay? This is not one of the better spectrum, but it matched my PowerPoint color scheme here. So this is how we know it's working. And so we can make the colors, and so the first thing we did was just, because it is a third order nonlinearity, it should go with higher power, see bigger effect. And so the first thing, of course, we just did was change the energy. 2 millijoules, we got this many, 3, we got this many, and by 4, we got the ones that I'm showing you. I think there's 16 there, and also some on the red side. So it worked from that point of view. It was a master's student working with me on this, and I actually went away on a camping trip with my friends and my family, but I told Fraser, I said, okay, you can't just do this. You have to also look at the effect of dispersion on it. So you have to now just leave it at the highest intensity and change the pressure of the cell. And so I went away, but he left a really great message on my home phone at the time. He said, Donna, you should be here seeing this. This is so cool. You're missing it. And it was true, because we never actually managed to get this data as nice again. But he took it, and I believe him. So what did he do? He decided on his own that in order to set up the experiment, he would do something quick and dirty first. He would have all the energy and the highest pressure we could put in the cell here. I should say that it is a slightly different, it's a different hollow fiber. It's a much smaller hollow fiber. Just to explain why, We had a big 250 micron hollow fiber, and so the only dispersion in that kind of fiber is just from the pressure of the gas. But we couldn't get it down to 0, right? The gas always has positive dispersion. But a smaller hollow fiber, and how a hollow fiber works is a regular optical fiber works on total internal reflection. A hollow fiber is actually the opposite. And so the physics of how a hollow fiber works is the same as if you're skimming stones on a lake. It actually is grazing incidence, and that's the way it works. And so the light just barely goes into the glass, skims along the surface, and comes back out. But you will actually get negative dispersion from this grazing incidence. And so you can counter the two dispersions by making them low enough. So that's the difference. So he started by saying, let's have all the pressure we can and all the energy we can. These are our two pumps. You can see we have this flat plateau. This is why at first we thought maybe it is like harmonic generation, even though it's not. And then he had the intensity, which of course we'd already done, and we got less orders, which we already knew. But then he went back to the full energy, and he went and said, let's do half the pressure. From a nonlinear optics point of view, these two pictures should look the very same, okay? Just from how big is the nonlinear effect, it should be the very same. And anybody can see that it's not the very same, okay? And so this, of course, is what was exciting, was the fact that you'll even see here, there seems to be this continuum or blob of spectrum underneath here, but not under the two intense pulses. These are not as intense, and yet we somehow seem to have it here. When we lowered the pressure, it seemed to move further out here. You'll also see that these are the green colors, and these colors are almost as bright as the infrared pumps going in. And so in the message that he left me, going out of the fiber is glowing green. It's not glowing white, it's glowing green. We're making so much green. We still haven't figured out that part, okay? So it's glowing green. But what we stopped to really think about is this part here. And this part here, we say we have red shifted shoulders, or we have this whole big continuum, and on the blue side, it's being cut into the continuum and leaving the red shifted shoulders. We don't know which it is. But we decided at the time that even though, as soon as we saw the previous results and we saw the 16 orders, I went ahead and got all of the prisms. We were going to compress each of the individual orders. We were going to time them all up. We were going to show that we had close to single femtoseconds. We've never tried that experiment yet because this stopped us. Both Fraser and I wanted to figure out what are these extra peaks that are showing up that nobody expected. And of course, the first thing you do is go back and look at everybody else's results who are also using shorter pulses. So far, it hasn't shown up in the people that are using nanosecond pulses. It's those of us who are using shorter pulses to see this. And what we found was that in this work here, I think it's the only one I'm going to show you, they were using different gas than us. They were using hydrogen and methane. So one of these is hydrogen, one of these is methane. So it's not the same gas. And yet, you can see here that they have these same sort of red-shifted shoulders showing up and the spikes on the other side. And red-shifted shoulders here and here. And there's other people's work as that. And I've talked to this group and said, what's going on? And they didn't know. And I talked to the other group that saw it. I said, you've got really big red-shifted shoulders. What do you think they are? And they hadn't thought about it. And so that's why we decided to think about it. I'm not going to explain it to you because when you're still working on something, it's very hard to explain even to yourself. So I'm not going to try to explain it to you. But I think that's where I'm going to end. Yep, that's where I'm going to end. These are the students and the postdocs that helped me. Thank you very much.